Hello guys, so this is the Unit 2 test review, and I'm just going to go through the ideas that are on the test here, so on this review. I'm going to try to do this as quickly as possible because I don't want the video to get too long, so I apologize if it does get a little longer at the end. But the idea here is that this is to prep you for the Unit 2 test. So the test has the topics of electric potential energy, electric potential or voltage, capacitors, resistors, circuits, lots of different circuits, so series, parallel, capacitors, resistors, and then finally RC circuits. So I'm not going to go through all the answers to the conceptual questions because a lot of them are covered in the problem, so they're to understand, to do the problems, you have to understand the concepts, but you should be able to read and understand these. If you do have any questions, just message me or ask me at some point so I can clarify what I mean by these ideas. So the first page is mostly the conceptual ideas. All right, so the first problem is given, and it says a 4 microcoulomb charge and a negative 4 microcoulomb charge are shown at these two positions. So those are the two positions. I just called this negative one charge 1, and I called this one here charge 2. So what we're trying to do is we're trying to find what is the potential difference at point A. So point A is where we're measuring the voltage. So the total voltage at that point is created by both of those charges. So we have the voltage from 1, and we're going to add the voltage of 2 together to get us the total voltage here. So the equation that we're going to utilize is V equals KQ over R, and we're going to do that for each individual charge. So the first thing we need to do is we need to figure out kind of what K is, what Q is, and what R is for each situation. So if we do for the voltage at 1, or from 1, K is always the constant, so that's 9 times 10 to the 9th. You can have that written down, or I'll give that to you. Coulomb's constant. Q is the charge. So for this one, it's going to be negative 4. And it's micro, so that micro is times 10 to the negative 6. So make sure you can convert for that take-home portion of the test. And then we're going to divide by R. So R is the separation between these 2 points. So this is where 1 is, and the separation is that diagonal line. So we need to figure this out. It just turns into a triangle. So it's the sides of the triangle is equal to the hypotenuse. This is basically a hypotenuse, so we're going to use the Pythagorean theorem. So it'd be like a squared plus b squared equals c squared. I just assume that you guys will know this relationship because it's a special triangle. So this is a 3, 4, 5 triangle. So it's like 0.3 squared plus 0.4 squared equals c squared. And when you solve for c, you get 0.5. So 0.5 is that distance that we're going to use. 0.5 meters is what we're putting in here for the R. So you put that in your calculator and you get an answer. That answer turns out to be for V1. I got negative 72,000 volts. So that's the answer for that one, from that charge being at that distance away. For V2, we're going to do similar work. It's a little bit easier because we don't have to do any math to figure out the separation. So it's still 9 times 10 to the 9th negative, or 9 times 10 to the 9th is K. Then we have to use the charge for this one. It's a positive 4. So we're going to get a positive voltage here, times 10 to the negative 6. And then finally, we're going to divide that by the separation. This separation here is just the distance going across. So that's just 0.3. So when we get that answer, you get a positive 120,000. And then to get the total, you just sum them up. So we're going to add the voltage at 1 plus the voltage at 2, which is what we said we we're going to do here to get the total voltage. And for this total voltage, I got a positive 48,000 volts. So that's the solution. That's what you should get for number 1. Number 2 starts talking about a parallel plate capacitor. They give you various information along the way. So it says 2 isolated copper plates, each of area 0.4 meters, carry opposite charges of magnitude 7.08 times 10 to the negative 10th coulombs. They are placed opposite each other in a parallel alignment with a spacing of 4 centimeters between them. And then we're going to solve for different things. First, we want to find what's the potential difference between the plates, so delta V. We want to figure out for part B, what's the magnitude of the electric field, so we're looking for E. Part C is just drawing a picture, so it's going to draw the electric field, so the direction of the electric field basically. So we're going to draw a picture, so it's going left, right, up, down. That's the question for C. Oh, that was supposed to be a D, but it doesn't really look like one. So let's try again. D says if we put a positive charge in that electric field, where would it go? So we're trying to say why it would move, what direction it would move, and why it would go that way. So first, let's kind of list out what we have. So 0.04 meters, that's the area squared. So that's 0.4 meters squared. For the second part, we know the charge, so that's Q. So the charge on the plates, it doesn't matter if you write it as positive or negative. One plate is positive, one plate is negative, is 7.08 times 10 to the negative 10th. So that's coulombs. And then finally, the separation or the distance between the plates, so like the distance going across, that's how far they're separated. That is 4 centimeters. So we don't work in centimeters, we work in meters, so we have to convert that. So if you divide it by 100, you'll get 0.04 meters. So that's a 4. Again, these answers are all posted online, so you should be able to follow along, but this is me talking through it. So for the capacitance ideas, we have 2 equations. So we have the physical properties that make up a capacitor, which is the permittivity of free space, which describes how the electric field moves in a vacuum. A is the area of the plates, and D is the separation between the plates. We also have the equation to define capacitance, which capacitance measures the ability of the plates to collect charge at a voltage. And again, this is a kind of fixed amount based on this physical construction, so this doesn't change. So for part A, we're actually going to use both these equations. So we're going to solve for the capacitance first. Another constant that you will be given or need to know is E naught. And E naught is that permittivity of free space. It's 8.85 times 10 to the negative 12th. Again, you don't have to memorize that. And the units that I did in it would be farads per meter. That's the units. Okay. So so if we put that number in the equation, and I'm just going to say this is C to save me a little bit of time. So instead of having to write that number out again, so it would be C is equal to the permittivity of free space times the area, which is 0.4, divided by the distance between the plates, which is 0.04. You will get your answer of capacitance, and that's like 8.85 times 10 to the negative 11th. And the units for a capacitor are farads. Again, usually it's like micro or pico, but that's fine. This is the answer is good. So, so that's the capacitance, but that's not what it asks for. It actually asks for the potential difference. Potential difference is voltage. So we're going to take this equation and solve it for V. So if we did this, basically these just trade spots. So delta V equals Q over C. So we're going to take this capacitance and put it down on the bottom. So this is the 8.85 times 10 to the negative 12, or times 10 to the negative 11th. And then for the charge, they told us the charge, that's the 7.08 times 10 to the negative 6 number. So when we divide that out, you get the voltage value, which is the answer to part A. So for part A, you should get a voltage of 8 volts. So that is the voltage across those 2 plates. For this one, we need to find for part B, we need to find the electric field. So you need to kind of use this voltage idea and the separation between the plates. So we had an equation pretty early on where we're talking about electric potential energy, and we used capacitors as the model. This equation, delta V equals ED. So we have 8 as the voltage, E is what we're looking for, and then the separation is 0.04. So we're going to divide both sides by 0.04 to get E. And you should get the electric field is 200. You could call it volts per meter. That's okay, or newtons per coulomb. It doesn't matter. They're the same unit. It just depends on what you want to write it on. This one, we probably write volts per meter because 8 is measured in volts and meters here, but it's the same idea. So that's your answer to part B. So answer to part A, answer to part B. Part C and D are more conceptual ideas, so this is where we'll cover some of the ideas here. So for part C, it wants to know what is the direction of the electric field. So if you remember back to last unit, electric field lines leave positives and go towards negatives. So the red arrows going across here are the electric field lines. So they should be equally spaced because it's a uniform electric field. So those lines is what you would draw in if this was your question. So it's going to the left. They're going to the left. Okay. Part D asks if you put a positive charge. So if we stuck a positive, let me get a different color. So if we put a proton or some positive charge in the middle here, it says which direction would it move. So the positive charge, if you think about electrical forces, is going to get repelled by the positive side, and it's going to be attracted to the negative side. So it's going to follow the electric field lines. So it would also move to the left. And you could just talk about the law of sines with like attraction and repulsion. So that's going to be the electric force is going to push it in that direction. So the electric force goes to the left on the positive charge, and that's going to make it move to the left. So that's good enough for what we're talking about in question 2. Question 3, again, a conceptual question. It's talking about two ideal parallel plate capacitors are identical in every respect, except for one has twice the plates as the other in terms of their area. So if the smaller capacitor has a capacitance of C, we want to know the larger one has a capacitance of what. So again, this is using that C equals epsilon naught A over D. So D and epsilon naught are the same. So this is, if this is 1, this is with area 1. If we double it, because we double the area, the capacitance 2 should be 2C. So it should be doubled because you've made this twice as big. So the result of that would be making, it would be twice as big. So capacitor 2 would have twice the capacitance as capacitor 1. All right, so it just doubles. The next question says the plates of the parallel capacitor are pulled further apart. So again, it's still the same equation, C equals epsilon naught A over D. And we want to know what happens to the capacitance. So if D gets bigger, what happens to C? This is in opposite parts of the fraction, so they are indirectly related. So if D gets bigger, C is going to get smaller. So the capacitance decreases, all right, proportionally to that. The last question says if the potential difference across the capacitors is constant as the plates are separated further apart, the charge on the plates does what? So we're looking for Q. So this is the idea of C equals Q over V. So this is, V is a constant. And as we change the physical makeup of this capacitor, we said we're increasing the distance, so the capacitance should go down. So we're trying to figure out what's happening to Q. So this number is decreasing. We have to change this number to make it mirror what's going to happen here if the bottom's constant. So the charge actually drops. So there's less available charge on those plates. So that is like using this equation for capacitance and the physical properties to describe how changes would affect the outcome. That's what we did in that introductory lab when we were investigating capacitors. So that's the first 3 questions. The fourth one, we're talking about resistors. In resistors, there was a resistance equation based on physical properties. So it's R equals P L over A. Just to talk through these different ideas, P is called the resistivity of the material. It's basically just describing how good of a conductor it is. So the better the conductor, the bigger this number is. I'm sorry, the more of an insulator it is, the bigger this number is and the bigger resistance. I misspoke. L is the length of the wire or resistor. So a longer wire would create a longer, a bigger resistance. And then finally the area, which I just like colored in the area of that one. If we had a like fatter wire or a bigger gauge wire, then this area would be larger. So the area part is talking about like the shaded in spots that I just drew. So as the area gets smaller, so as this area gets smaller, the resistance gets bigger. So those are the kind of concepts. So these questions are based on that. So it says 2 copper wires of equal cross-sectional area. So the A is the same. One wire is 3 times the length of the other. How do the resistivities of the wires compare? They're both made out of copper. So if they're both made out of copper, it's the same number. So they're the same. So doing anything with those values, whether L or A changes or doesn't change, resistivity is a physical property of the material. So it's just a number. It's the same for copper. Now we're going to change the length, and we have 2 copper wires of equal cross-sectional area. This time we're making L get bigger. So if L gets bigger, R gets bigger. So it gets bigger. It would actually get 3 times bigger if you wanted to talk about it. So it's 3L. So you're multiplying it 3 times this whole thing. Everything else stays the same. P and A are the same. The last part here, it says 2 copper wires of equal length. So length staying the same. One has twice the cross-sectional area of the other. So the area is doubling. So the resistance is actually cut in half. That's what happens for that one. So that is the relationship, because as A increases, R decreases. Okay, so those are the conceptual ideas that go along with the physical properties of a wire. The next couple questions, we're talking about capacitors in series and parallel, and resistors in series and parallel. So these will go, I think, pretty fast. So for number 5, it says 2 capacitors are connected in series, and these are their values. If a voltage source of 90 volts is applied across the combination, find the equivalent capacitance and find the total charge stored in the configuration. So I like drawing the pictures. So that's my battery. And I need 2 capacitors in series. So capacitors are 2 lines of equal spacing or equal length. The battery has 2 different lengths. So if you look at these 2 ideas here, so this is my voltage, which is 90 volts. We could call this capacitor 1 and capacitor 2. It tells you the values here, so I won't worry about writing them again. When they're in series, it's one right after the other, so it's one path, right? So what we need to do is we need to figure out what is the equivalent capacitance. So in series, capacitors in series, you do the inverse of them. So it'd be 1 over C1 plus 1 over C2 to the -1 power. So that's what you would have to do. So I'm not going to convert anything here. I'm just going to do 1 over 4 plus 1 over 7. And the answer will just be in microfarads. We'll convert after we get to the point where we need it in regular farads. So if you put that in your calculator, as I have listed on the page, this turns out to be like 2.55. When capacitors are in series, you are essentially separating the 2 plates more, so that distance got bigger. If the distance gets bigger, the capacitance gets smaller. That was our relationship. So 2.55 is less than 4, it's less than 7, so it's a smaller total capacitance overall. To find the total charge, we're going to use the C equals QV equation, or Q over delta V. We need to solve for Q. So if I solve that, it would be Q is equal to C times delta V. The capacitance we got is 2.55. It's microfarads, so I'm going to convert it here. So 2.55 times 10 to the -6. And then we're going to multiply that value times the voltage, which is 90. So when we solve for Q here, you should get 2.55. No, sorry, 2.29. Sorry, I forgot to multiply by the 90. 2.29 times 10 to the negative fourth. And that's right on the answer key. I just spoke it incorrectly. And that will be coulombs, which is charge. So that is the first one. That's capacitors in series. Again, the total capacitance goes down because you're increasing the distance. So if you think about it in terms of this equation, E naught over A D, the separation is increasing, so the capacitance drops. The voltage is held the same, so again, the capacitor or the charge has to drop to match or mirror the capacitance. All right, now we have the same capacitors in parallel. So again, the picture hooked up to the same battery. Parallel meaning that everybody has their own loop. So in this one, effectively, you're allowing more spots for the battery to charge more spaces on the plates. So the area is effectively getting increased in this idea. So in the capacitance, E naught over A over D, A is increasing, so the capacitance increases. So we would expect a bigger capacitor. So when they're in parallel, all you do is add. So it'd be C1 plus C2. So it's just 4 plus 7, which is 11 microfarads. So the total capacitance here is bigger than the individual ones. Capacitors are essentially the opposite of resistors. So if you remember one or the other, you actually remember the other type as well. So that's part A. Part B wants the total charge. So it's again the same kind of work. So C equals QV or delta V. And we're going to solve for Q. So it's C times delta V. Delta V is still 90. C is this 11 times 10 to the negative 6. So if you put that in your calculator, you will get 9.9 times 10 to the negative fourth. So we have more charge in this one for the same voltage, so it has a higher capacitance. That's the concept. All right. So effectively you're taking these individual plates and putting together and making it a larger plate so it can get more charge on each side than you can in the other one. All right. So that was 6. 7 and 8 are the same kind of concepts, except it's talking about resistors. So again, I'll draw the picture. So we have our battery hooked up to series resistors. So that's our picture. So it's a 9 volt battery, and it's a 5 and a 10 ohm resistors. To get the total resistance or equivalent resistance, you just add in series. So it would be 5 plus 10, which is just 15. So 15 ohms is the total resistance. That's part A. Part B wants you to fill in the table. So this is a little bit more work than what we had to do in the last problem, but it's not so bad. So for part B, we need to figure out, okay, what's the total current in this circuit? So the total current, we're going to use Ohm's law. So V equals IR, or I equals V over R. And we're going to use the total value. So the 9 volts divided by 15 ohms will get us the current. So that amount of current is equal to 0.6 amps. Because it is a series circuit, there is only one path for the current to move through the loop. So that means that the total current is equal to the current in the first resistor, or the 5 ohm resistor, which is also equal to the current in the 10 ohm resistor that goes through the 10 ohm resistor. So both these values in this chart are 0.6. So that's basically all you need in the chart to get to the other parts. So we're going to use V equals IR and solve for V. So I have I and I have R for both of these. So 0.6 times 5 is 3. 0.6 times 10 is 6. If I add them together, it should get me the total voltage. 3 plus 6 equals 9. So we're good for that part. For the power equation, power is equal to I times V. So I just have to multiply these two numbers. So 3 times 0.6 is 1.8. And then 6 times 0.6 is, I'm sorry, yeah, 6 times 0.6, I have a typo. I apologize. I'm fixing it now. So it would be 6 times 0.6 is 0.36. 6 times 0.6 Yeah, it's 3.6. I did the one step beforehand. So we're going to add these together to get the total power. So the total power here is 5.4. I accidentally wrote 5.4 watts in this box, so that's a typo. I'll go back and fix it or add a note to the document. So that's the total power. If I wanted to check the total power, I would use the total current times the total voltage. So the total current was that 0.6, and the total voltage is 9. 9 times 0.6 gets you 5.4 again. So I apologize for the typo. I will fix that. The next one we have in 8 is a parallel circuit. So again, it's just using the rules for parallel. If I draw it out, resistor 1, which is 5 ohms, resistor 2, which is 10 ohms. It's hooked up to the same 9-volt battery. So in parallel, the total resistance, you do the inverse rule. So these are like capacitors in series. So it'll be 1 over 5 plus 1 over 10. And then you have to do to the -1 power. So if you do that, you will get the total resistance is 3.3, and it's repeating ohms. So that's part A. For part B, it's a little simpler on this one because for parallel, the rule is the voltage total of the battery is equal to the voltage of each one. So it'd be the voltage across the 5, which is the voltage across the 10, because each one is its own loop. So if you use Kirchhoff's rule, if we gain whatever 9 volts across the battery, we have to lose 9 volts across each resistor. So those are all 9s. And again, it's the same kind of application. So this is 9 and this is 9. So in order to get I is equal to V over R. So I'm going to take 9 and divide it by 5 here. And this one would be 9 divided by 10. So 9 divided by 5 is like 1.8. 9 divided by 10 is 0.9. If we added those together, we'd get 2.7 amps. And that should be the total current. If I wanted to check it, I could do the total current is equal to the total voltage divided by the total resistance. So this would be 9 over 3.3 repeating. And if you do that, you will get 2.7 amps. So that checks out. That means that we did that part right. For power, it's just I times V again. So I times V, 9 times 1.8. I got 16.2. That seems right. This would be, again, watts, the units I have up there. And then 9 times 0.9 is 8.1. If I add those up, I get 24.3 as the total power. If I wanted to check it, I could do the total current, which is 2.7 times 9, which will get you the same answer, the 24.3. So hopefully that's making sense for you guys with resistors. I think series and parallel resistors, after you practice them a little bit, are pretty straightforward. So then we have a combination circuit, and then we have our last one, which is an RC circuit. We're at 28 minutes, almost 29 minutes. I'm going to keep going. We're going to finish it up, so I'm sorry this video is a little bit longer than most, but it's just a video that you have to watch. It's not necessarily for a grade. So in this one, we have 4 resistors hooked up to a battery, which is only 2 volts. I'm going to label the bulbs here. So I labeled them A, B on the top line. So A is the 2 and B is the 4. And then C, D for the 3 and the 9. So I'm just going to write their letters in here. So that was bulb A, or resistor A, resistor B, resistor C, and resistor D. So what we need to do is we need to find the equivalent resistance and again fill in the chart. So to find the equivalent resistance, you need to kind of combine resistors. So I would say RA and B are parallel to each other. You could have also started with RC is parallel to RD. So it's the same kind of relationship. Or I'm speaking incorrectly. Let me start over again. Sorry. RA is in series with RB, and RC is in series with RD. So that makes sense because they are on the same line. So the current that goes through this one will be the same current that goes through B, and then the same current that goes through C is the same current that goes through D. They are not the same currents, by the way, but just to make sure we understand it. So the math for this is pretty simple. For series, you just add. So RAB would be 2 plus 4, which is just 6 ohms. For CD, it would be RCD, and that would be 3 plus 9, which is 12 ohms. So we have those. I'm going to redraw the picture. So when I redraw this, we still have the same 2-volt battery, but this time we have 2 branches that have 1 resistor on them each. So resistor AB on the top and resistor CD on the bottom. So when I come out of that, I have a junction, it comes back to the battery, and we're all good. So, so again, this one is 6, and this one CD is 12 ohms. So now we have to find the relationship between AB, resistor AB, and resistor CD, and they are parallel. So that's what I was speaking about. I was looking ahead. So AB is parallel to CD, so this is where we do the inverse idea. So our total, or the equivalent resistance, would be 1 over 6 plus 1 over 12 to the negative 1. If you do that and you flip it over, you get 4. So 4 ohms is the equivalent or total resistance. The circuit will change into a circuit that looks like this. So that's my battery, that's my resistor total, and we're in pretty good shape. So, so this is 2 volts and this is 4 ohms. If I wanted to check for the current and figure out the current, I would use Ohm's law. So I would figure out, okay, what amount of current has to get around there. If you used Ohm's law, the total current is the total voltage, so that's a T, VT over RT. So it would be 2 over 4, which would be a half. So we have a half amp of current going through the circuit. So if I started out here, let me get a different color. So this current that leaves the battery and starts making its way to this junction point is 0.5. So 0.5 amps. What comes out of that is also 0.5 amps. So we can use that Kirchhoff's rule relationship later on. The 0.5 splits, so part of it goes on the top, part of it goes on the bottom. More is going to go on the top because it's got a lower resistance, and less is going to go on the bottom because it has a higher resistance. But the easy way to kind of work this out is to figure out the voltages. So we're going to figure out the voltages. And because it's parallel, if we look at this circuit, these are parallel. So they have the same voltage of the battery. So the voltage across AB is 2 volts, which is also equal to the voltage across CD is 2 volts, and the total voltage is 2 volts. So it's all the same amount of voltage because these are all parallel. So we can solve for IAB, and we can solve for ICD in the same way that we just did to find the total current. We could also use the junction rule and just get one of these and subtract, but let's just work through it this way. So it's the voltage over the resistance. So this would be 2 over 6, which is a 1/3. I'm just going to leave it as 1/3 because that's easier as a fraction than a decimal. As a decimal, it's 0.3 repeating amps. You could write it out like that. That's fine. And then for voltage CD, it'd be the voltage of CD divided by the resistance of CD. I didn't write it up here, but this is AB and AB. So I'll go back and put that in. So the total voltage is still 2 across that, and this time we're dividing by 12. So that's going to get you 1/6. So like we predicted, we would have more current going through the top than the bottom. 1/6 as a decimal, I think, is like 1.6 repeating. I think that's how it works out. Yep. So this is I'm sorry, not 1.6, 0.16, and the 6 repeats. So if you add those together, you'll get 0.5. Because if you make this is like 2/6 plus 1/6 would be 3/6, and that's a half. So that works out. So I'm just going to write it as thirds and sixths. So 1/3 and 1/3. Because they're in series, these currents are the same. So we drew the picture here. So if I have 0.333 repeating going through the this branch up here, that's the red section up here. That's how much current goes through AB. That's how much individually goes through A and how much individually goes through B. For the one below it, for CD, that's the blue, where I drew the blue here. And that's going to be 0.16 repeating, or 1/6 going that way. So these are 1/6. Once you have those all filled in, then it's the same kind of math that we did for the voltage and the power before. So if I multiply 1/3 times 2, I get 2/3. 4 times a third is 4/3. 3 times a sixth is a half, or 3/6. And then 9 times 6 would be 3/2. If you add all these up, you should get that should make sense for the voltages across each piece. And then you're going to do the voltage times the current to get to the power. So 2/3 times 1/3 is 2/9. 4/3 times 1/3 is 4/9. 1/2 times 1/2 times 1/6. We'll just leave it as I'll say this is 3/6. It'll make the math easier. So 3/6 is the same as 1/2. 3/6 times 1/6 is 3/32, or 1/12 if you want to do it that way. And then I think I wrote that wrong on the last one. Let's check this out. So this should be 9 times 1/6. So this would be 9/6. I'll write that again, 9/6. And then 9/6 times 1/6 would be 9/36. If you add all those up, you could do it as a fraction. This would be like 6/9, because 2 plus 4 is 6. And then you have 12/36. So 36 is the lowest common denominator. Again, this is a lot more fractions than what I would give you on the test. Just use your calculator. It'll work out fine. But if I multiply 4 times 6, that is 24. And 4 times 9, that is 36. And then when you add this up, 12 and 24 gets you 36/36, which is just 1. So that's 1 watt. If you check the power equation, power total should be the total current times the total voltage. It checks out because we had the total current as 0.5. That's what we got up here. So it's 0.5 times the total voltage, which is 2, which again supports our idea that this is 1. So that only checks out if we did all these other things right. So, so that one is now complete. All right, last one we have here is a RC circuit. So the video and lesson in this in class today is dealing with RC circuits. So it's a 2 microfarad capacitor, so that's C. It's connected to a 12-volt battery to charge. So the potential difference, or delta V, is 12. And then it's discharged through a 4 mega ohm resistor. So mega is times 10 to the positive 6, or like a million. And it's a resistor, so that's R. Okay. So we're trying to find the time constant. The time constant is this Greek letter tau. So it's R times C. That's how you calculate it. So R is 4 times 10 to the 6th, or 4 million. And C is 2 microfarads, so that's 2 times 10 to the negative 6. The negative 6 and positive 6, when you multiply two numbers, the exponents just add. So it's positive 6 and negative 6, they just cancel. So it's really 4 times 2, which is 8. So it's going to be a time constant, so it's measured in seconds. So 8 seconds is the time constant that the capacitor discharges at or charges at. It's the same. So for part B, it wants to know what is the magnitude of the charge on one plate. So we've done this a couple times already. C equals Q over delta V. So after it is charged up all the way, what is the magnitude of the charge? So we know the capacitance, and we're looking for Q. So Q equals C times delta V. So again, C is that 2 times 10 to the negative 6. And V is the voltage, so that's 12. So it's really 24 times 10 to the negative 6, or 24 micro coulombs. That's a 6, and that's coulombs, C. Part C wants to know what's the original current. So the original current, I.O., is based upon the voltage and the resistance. So basically, this is just Ohm's law. So it would be the total voltage, which is 12, divided by the total resistance. So that's the 4 times 10 to the negative 6. So it's going to be a small amount of current. That's supposed to be a 6. So when I divide that out, I get 3 times 10 to the negative 6 amps. So it'd be 3 microamps, which is a really small amount. All right. Part D asks, what is the voltage across the capacitor at 11 seconds? And then part E wants to know what's the current in the circuit at 11 seconds. So we are discharging because we are starting out with like we have a battery. I'll draw this out. So we have a battery hooked up to, that's the battery, so that's the voltage. It's hooked up to a capacitor, so we have parallel plates, that's the capacitor. And there's a switch here, so we can change it. And originally when it's hooked up there, and then we have our resistor on this side. So this is R. And we basically have a switch. So if you imagine I have this red piece of metal and I can move it to the left and connect it or move it to the right. So when I first have it, it's connected to this loop. So this battery charges the capacitor. So that's when it's charging up. All right. And then later on, we're going to discharge it. So when we discharge it, we switch the switch over this way. We move it to the right. This no longer is powering anything. It's the capacitor is powering the resistor. So the capacitor is sending current through this circuit and sending the charge through the resistor, which is going to power the resistor. And as time goes by, there's less current and less voltage. I'm sorry, there's less charge on the plates because the charges are moving. That's what current is. And because of that, there's less voltage. If there's less charge and less voltage, then the current drops off, and so does the voltage. So the equation to calculate part D is the voltage. So it's the change in voltage of the capacitor is equal to the original voltage of the capacitor, so CO, original, times this idea of E to the negative T over tau. So just to break down these things, so we're looking for the new voltage at a certain time. So that's what we're looking for. That's the left side of the equation. This is our original voltage. So the original voltage of the capacitor is the voltage of the battery. So that's going to be 12. So that's 12. I think I said it was 24. Let me make sense. Okay. So I made a mistake. I think I might have had it incorrect again. Sorry. Second mistake. So I'll fix this one too. So it should be 12, not 24. 12 is the voltage of the battery. And then you're going to take the idea, and E is a number. It's based on natural log, and it's an exponential decay is what it is. So E to the negative, the time that it is 11 seconds. So that's the time that we're measuring it at. And 8 seconds is our tau, or our time constant. So when you put that in your calculator, and I'm going to redo that again, I think it's 3.03, but it's 12 times E to the negative 11 divided by 8. Yeah, it is 3.03. So I did have it right, and then I changed it and then posted it. So I apologize for that. So it's 3.03 volts. That is the new voltage. So as time goes by, the voltage drops. So it looks something like this, like it's an exponential decay. So the curve goes like that. So it starts out at the maximum voltage, right? That's the voltage of the battery. And as time goes by, after certain time constants, so T1 or 2, T2 or tau2, So like this is 8 seconds, and this would be 16 seconds, and then 24 seconds. After like 3 or 4 of the tiles, you're almost down to nothing. 5 will get you to 0. So 5 time constants based on this exponential decay will get you down to no voltage. So that's part D. The last part, sorry, it's a really long video. Last part is essentially the same equation. It's just using the current instead. So same kind of idea. It's I equals I naught E to the negative T over tau. Again, these are both discharging. Charging has a slightly different equation for voltage, but the current is still the same. That's the same equation. So we're going to use the current idea. So that's this number. I didn't mess this one up. It's 3 times 10 to the negative 6 times e to the negative 11 over 8 again. And if you do that, you get 7.59 times 10 to the negative 7th. So, and that's going to be amps. So again, it has dropped a lot. So it went from 3 times 10 to the negative 6, which is a small amount, to a factor of like 10, almost 20 less. So it is a much smaller value. All right, so I'm going to stop there. That's 45 minutes. It's a really long video. Sorry about that, guys. I will post the corrections as well. Talk to you guys later.